our next speaker is Wolfgang Tittel. He's professor and at QuTech, but also he has some professorship at University of Geneva and the Schaffhausen Institute of Technology. And he will tell us about quantum communication coming from the lab to the real world infrastructure. Wolfgang, the floor is yours. You can share your screen.
Good morning, everybody. Good morning, Jack. Thanks a lot for the nice introduction. I hope you can hear me. All right, let's assume that. As we have heard already a couple of times today, a lot of different countries, the European Union, the USA, China, they're all thinking about the implementation of large-scale quantum networks. These are networks in which some type of quantum information processing will take place in network nodes, and then photonic channels, either optical fibers or satellite-based links, will be used in order to allow the communication of qubits from one node to the other, or the establishment of entanglement between these large-scale networks. In the next 20 minutes, I will try to give you a little bit more of an idea, a little bit more information regarding how one could create such networks, how far we are, and how we should do what we could do in order to really get to where we would like to be. And I will start with splitting this topic into two parts, into two different types of networks. And the first one type is generally referred to as so-called trusted node networks. And the goal of these networks is only to establish secret classical bits. Yeah, we use qubits, we send them from one point of the network to another one, but the idea is to create secret bits through quantum key distribution. And these bits in turn can be used for quantum secured communication, ideally combining of this key with a one-time pad allows us to make sure our messages cannot be listened in by anybody else. Now, it turns out this technology is currently limited to around 100 kilometers of distance for optical fiber. And if you would like to build larger networks over larger distances, and I have shown here an example of a vision of the Chinese network, where they really try to span a total of 35,000 kilometers using a combination of fiber and free space links within the next 4 years or so. Well, if you would like to go to networks like that, currently the only possibility is to use so-called trusted nodes. Yeah, so let's say we can establish a secret key between here and here using quantum communication, and we can establish another secret key between the same node here and another node another 100 kilometers away, and so on. So if we have these secret keys, what we can do then is pass a secret message hop by hop from one node to the next. So at this node, it would be encoded using the key that this node shares with this. Here it would be decoded, re-encoded with the key that this node shares with this node, sent over here, decrypted, re-encrypted, and so on. Yeah, so that's already quite useful, but we have to keep in mind that the message would become clear text in these nodes where it would be decrypted. Of course, one wouldn't do this. One would always add some kind of classical cipher in order to ensure we still have the classical security in these nodes. But be still aware that even though you add this classical cipher, you don't have end-to-end quantum security as promised by quantum key distribution. And also the application of these networks, the usability is limited to those applications where we only want secret classical bits, not qubits. I will come back to this on one of my next slides. And so I've mentioned already the really incredible Chinese vision, but I would also like to mention that the European Union, at least the 27 member states right now, there is a project, the so-called Euro QCI, the Euro Quantum Communication Infrastructure Initiative, building on the OpenQKD project that aims to create a large-scale quantum network across the EU 27 countries. The timelines are this year. The focus is on the development of European quantum key distribution devices and systems, development and deployment of national quantum key distribution networks, and the building and devising of testing and certification infrastructure. And then after that, we will look into cross-border links between national networks, different national networks, and also about the creation of the link between the space segment and the Earth fiber-based segment. Yeah, and the plan is that this network will be fully operational in a couple of years from now in 2027. So I took a little bit of time to find some startup companies who really create quantum technology. And this is what I have found in the last day or the last 2 days or so. So maybe it's not complete, but I think it's quite complete. And there are a couple of interesting things. So number one, there is QuTech as the front runner who has started activities in the area of quantum communication already 20 or so years ago, but they are known for their quantum random number generators and also for their QKD systems. I think after that, there was Single Quantum, who creates single photon detectors. And then for a long time, I think there was not much. And right now, what we witness, is a large increase of startup companies. Interestingly, a lot in the UK, and this is probably to be traced back to the fact that the United Kingdom has started their quantum programs that have the goal to bring closer together academic researchers in industry. They've started these programs a little bit before Europe has started this, so the flagship programs, for instance. Yeah, so we witness here already a large increase of startup activities, and I hope the same thing will happen also in the rest of Europe and in Switzerland. It is also noteworthy that with a very few exceptions, all these companies build what you can call traditional quantum technologies. I do realize there is a little bit of clash in the traditional and quantum, but what I mean with that, companies based on or focusing on the development of single photon sources, single photon detectors, quantum random number generators, and quantum key distribution systems, not yet the type of technology that we require in order to build the second type of quantum networks, which I like to refer to as fully quantum enabled networks, or also the quantum internet. Yeah, there the goal is different. The goal is not to establish secret keys or secret classical bits, but the goal there is to distribute long-lived entanglement between, well, hopefully at some point, any 2 points on Earth. Yeah, and this will mean also we need other technologies such as quantum repeaters. And this is something I've tried to depict a little bit here. So again, we can only send qubits or establish entanglement directly over, let's say, 100-kilometer long links, if I talk again about optical fibers. But in this case, we don't make measurements at this point here of a photon that comes from this side and maybe a photon that comes from this side. Here we make a joint measurement of the 2 photons, each of which belong to a different elementary link. And this measurement right now allows us, together with some other things, allows us to swap entanglement to quantum nodes that can in principle be arbitrarily far away. Yeah, so it's different technology. It's more complicated. It's by far not as mature as the other network that I've discussed before, but there's a lot of promise in this technology. For instance, we could create quantum secured communication links that are device independent, where we don't need any trust into the internal functioning of the technology inside the nodes or in the technologies themselves. Yeah, we can think about blind quantum computing, where we may want to send a computational task to a remote quantum computer. And now we can do it in a way that neither anybody who tries to tap into the communication link nor the quantum computer itself will be able to figure out what that task actually is. And I quite like this as an application. We can also think about distributed networked quantum computing. We can think about distributed quantum sensing, such as building optical telescopes with a higher resolution or synchronized atomic clocks. So there's a lot of possibilities that we don't have by resorting to quantum networks that simply allow the distribution of classical bits. As I said, it's still at an early stage of development, but there is a lot, mostly academic research with large clusters in almost all developed countries. So in Europe, why is this so more difficult? Well, the difficulty here is the large number of heterogeneous components that we require to build such a network. Yeah, here is a sketch coming. This is NetSquid, that's an application development at TU Delft. So what we see here are so-called AND nodes where we want to have qubits with which we can actually calculate. So these are often single atoms, single ions, maybe superconducting qubits. And the important thing is if they will be embedded into a network, well, they need an optical interface. They have to be able to talk to a telecom fiber or to a satellite-based link and emit photons that can be transmitted over these transmission lines. Yeah. We also need quantum repeaters. These are devices that allow us to extend entanglement across neighboring elementary links and therefore create entanglement between arbitrarily far away nodes. These repeaters Well, I think the best way of doing this is to use large ensemble of ions or atoms, because we would like them to be able to store a large number of qubits, like the hard disk in our computer also should store a large number of classical bits. Yeah, so we have yet another type of material, again, with a requirement for an optical interface. We also need photons at a wavelength that interact with these atomic systems. These are not necessarily the same photons for the ensembles and for the individual atoms or ions that we require for individual nodes, but they could be. Yeah. We also need photons at telecom wavelengths, because if you want to send them over a long distance across the Earth, well, telecom wavelength is the best for optical fibers. And for satellite communications, it could be telecom. Right now, it's mostly 800 nanometers, I think. I'm not sure yet what the final decision will be, or the final wavelength will be. Yeah. Now we see we have a lot of heterogeneous components, but we need these technologies to become compatible. We have to make sure that everything can work together. We need to make sure that the physical properties, the wavelength of the photons that are being emitted, the bandwidth, the waveforms, and so on, they're all compatible, and that's a very difficult task. We also have to make sure that the environment in which these different bits and pieces are operated are compatible. There's lots of different things in the quantum repeaters, for instance. Some of these may require a temperature of 1 Kelvin, others 100 Celsius, so they cannot be integrated on the same chip. But it would be great if we found a way to get there. Yeah, so integration is an important task. We need to make it scalable. We need to be able to mass produce these technologies. We need software control. And then we have to also think about standardization, certification, training of the workforce, and so on. So it's quite a complex task. In Europe, this is currently addressed by the Quantum Internet Alliance. It's one of the quantum flagship projects. And the goal of KIA is to develop a blueprint for a European based quantum internet. So that's the internet that allows the distribution of entanglement. And what we are doing there is that we develop, integrate, and demonstrate all the functional hardware and also the software systems. So we're looking into the creation of these AND nodes. We're looking into the creation of quantum repeaters. We're looking into the communication between those two. And hand in hand with that, we are also looking into the realization of a software stack inspired by the telecommunication software stack that allows control and the running of applications in a platform-independent manner. Now, how far is the field? How far are we? I've listed here a couple of milestone experiments, my personal preference, that show a little bit the progress and what we have done. Yeah, so we have heard already about an experiment that showed the distribution of entanglement from a satellite, and then it turned out that the two photons that are entangled, they received on the ground in China somewhere at a distance of 1,200 kilometers away. Yeah, so that's quite remarkable. This was indeed a real-world implementation over here. It was not better than direct transmission because it was direct transmission. There was no quantum repeater involved. And it was also not meant to be scalable in the sense that we can concatenate several of these links in order to go even to longer distances. Yeah. There was a demonstration back at the University of Kavli in my own group a couple of years ago about quantum teleportation across a metropolitan fiber network. Again, not better than direct transmission, not scalable, but real-world demonstration. There's a lot of activity in the development of quantum memories, which are a subsystem for quantum repeaters. There was very recently a demonstration where people from Harvard and the MIT demonstrated that it is possible to do transmission better, to get better scaling in the transmission of qubits than what you would get without quantum repeater technology. So this is what people refer to as the repeaterless bound. In principle, scalable, yeah, better than direct transmission. Scalable, not yet. The technology was not such that you can concatenate several of these links, and it was also a demonstration in the lab. Yeah. There was another demonstration about an elementary quantum repeater link. In principle, scalable, but not yet good enough to beat direct transmission. As I said, it was in the lab. And there was also recently the first demonstration of a 3-node quantum network in Delft, again, not inside the lab. So what you see here is that basically all the key elements are there. But as I said, they are not necessarily compatible. The wavelengths are different. The bandwidth of the photons are different. The operational conditions are also different. So what do we have to do in order to get where we want to be? Well, It's obvious we need interaction between people with different skill sets and different mindsets. And what I mean with that is, well, we need academic researchers. But this field is not yet sufficiently mature that we know exactly where we want to go and that we can already talk about precise milestones and roadmaps, and we have to develop these type of technologies or achieve this type of performance. I think there's still a lot of fundamental research, so academic researchers are still key. But we also need people from the R&D departments, engineers working in private companies, because we need stable and reliable subsystems out of which we can create larger systems and out of which eventually create the quantum internet. This is not what happens in academic labs. For this, we need a different skill set. We need a different mindset. We do, of course, need funding and funding programs. Otherwise, we can't get together. And we need also input from stakeholders who have applications in mind and with whom together we can develop applications and we can develop and fine-tune the necessary technology, similar to what is happening in the Open QKD project right now that focuses on quantum key distribution. Yeah, and all that together would lead to workable technology. Now, how in detail can you create this interface, the joint work, the collaboration between these different groups? And I will just briefly mention 3 different approaches that I personally have been involved with. One is that you can create joint institutes where academic researchers and engineers, R&D personnel, are working together on a daily basis on the same type of technology. Yeah, this is what, for instance, is happening in QuTech with quite a lot of success. You can also think about a model that I've experienced back in Canada, where there are so-called industrial research chairs, where the government co-funds or leverages cash and in-kind contribution from a company with the goal for that company to work together with a particular researcher or with a small number of researchers. Yeah, so that also brings people together with funding and together with the different mindsets. And at the end, well, you certainly have to build large consortia with complementary expertise, as it has happened, for instance, in KIR. Altogether, I think there are 26 different partners, 13 from academia and 13 from industry. All right, and with this, I come to the end of my talk. And I would like to thank you for your attention. And I'm waiting for questions.
Thanks so much, Wolfgang. You were able to explain us in understandable words what a quantum internet and what quantum network is. Even myself, I couldn't understand. That's a good thing. And we see how complicated it is to have these things compatible. And there are so many different technologies that we need some standardization and compatibility. And there is one question on that from the audience. How do you see the possibility to create this standardized quantum network with compatible elements? What should we do now exactly?
Yeah, so you can think of 2 approaches. So one is just go on with what we do, find different devices, and then think about the interfaces we have to put in between in order to make these devices talk to each other. Yeah, we can think about a quantum frequency conversion to move a qubit from a photon at one wavelength to another one. This is possible, but all of these devices are complex. All of these devices add loss. So this is not my preferred approach. I think it would be better if we had one device or one type of material, let's say, that allows us to do everything. And my personal preference there are rare earth ion doped crystals, because they are suitable for quantum repeaters. They are suitable for single photon sources. They are suitable in the same manner as we have heard before for quantum computing, in the same manner as NV centers for quantum computing. It is still early in repeaters. We have shown already their work. The other fields are still a little bit more early, but I think they have it all. And this is really what I think, where I would like to really focus my work on in the next years. Because I'm really, the more and more I work with them, the more and more I'm convinced that this is really the type of material that has it all.
Okay, and do you think there is a mismatch between, we are speaking about the quantum network, something which is, let's say, real, but the missing elements are things like the main ones, so the quantum repeaters, quantum memories, as you've shown, they are demonstration, but sometimes in the real world, sometimes in the lab. But still, there is a lot of development for having these key elements ready for being implemented in the infrastructure, no?
Mm-hmm. There is a lot of development. Right now, the efficiencies of most of these components are such that if we put them together, well, we have all repeater elements together, let's say, but we don't do better than without a repeater. Yeah, so it's an important first step. So the first step is just quantum communication, no repeater at all. The next step would be quantum communication using a repeater, but it will not necessarily be better than without a repeater. That's where we are right now. Yeah, but we have already the elements. We understand how they have to work together. We understand the performance that we can get out of them. Yeah, and now we have to make sure that we get to the performance that is beneficial to quantum communication links, so that at the end we can indeed increase the communication of qubits and entanglement above the distance of 100 kilometers or so.
Okay, let's take the next question from Natasha Tom. There are two questions related. How do you see the integration of the elements created by all these companies you've mentioned? And the related question is, are there consortia for making this company working together?
Yeah, so there are, so in Kia, for instance, companies are working together, but so far these companies that are working here are companies who provide, let's say, lasers or cryogenic systems, a lot of systems that we require to run our quantum technology, but it's not directly the quantum technology. Yeah, so there are no, with one exception, I think QFox, that's a company who focuses on something that is far out, which is a quantum transducer, which allows mapping of qubits between photons and the superconducting qubits. This is the only company that looks at technology that is not yet, well, that is not relevant or not necessary for the current quantum networks. Yeah, so right now companies are, but they all have their individual product, the same as they had before. They try to stabilize it better or make it a little bit less noisy, a little bit smaller, a little bit better suitable for what we have. But it's not yet that we're all working, that all companies work together on the same thing. And I'm also not sure if this will, if this can happen. I think everybody has his niche, and at the end we have to make sure that these things are all developed hand in hand, so that at the end they're coming together.
Okay. Coming back to the repeaters, at the time being, which company are the most advanced with this technology that might be integrated in the network? And with which technology?
Yeah, so for repeaters, I don't think this is yet in the realm of industrial research. People look at single photon sources, which can of course become relevant for repeaters, but the properties are normally optimized for the first type of network. The properties of single photons, if you want them to be used in repeaters, are a bit more complicated. Photons need to be indistinguishable. That is not necessary for the other networks. Yeah, so far, at least in Europe, there are no companies yet, to my opinion, that really looks into that, with the exception of QFox, which is a really just newly funded company in Delft, which looks into the transduction of qubits between different wavelengths, RF and optical. Otherwise, companies in the field of quantum repeaters and large-scale quantum networks, I don't think there are any yet in Europe. There may be some in the US, maybe Carl Williams, who's the next speaker, can talk about this at some point. But in Europe, I think it's an early stage. A good question, of course, is when does it make sense to start that? How long into the future should companies look, or can companies look? Is it already the time to start thinking about technology that will become relevant only, I don't know, maybe in 5 years or so from now?
Okay, many thanks for all your answers.